So, hi everyone, my name is Bernie and I'm a PhD student of Mauricio, and today I'm going to be telling you a bit about my project, which is looking at flavor anisotropies of high energy astrophysical neutrinos. So just to give you a bit of a sense of what we're talking about, I'm talking about high energy astrophysical neutrinos with energies of TeV to PeV. In particular, the IceCube ones are like 10 to the 4 GeV to like 10 to the 8. They originate from high energy hadronic processes that are extragalactic and have baselines of about a gigaparsec. And we heard a lot about those processes over the previous couple of talks. But it turns out that they have a rich phenomenology for physics beyond the standard model. And I'm going to delve a bit more deeply into that in a second. But first, I want to introduce that IceCube has already seen a flux of high energy astrophysical neutrinos. And we've also heard a bit about how this is done. Neutrinos come in as mass eigenstates over their long baselines, but they interact with us as flavor eigenstates and are importantly detected as morphologies, which is like a separate basis that are correlated to flavor. So cascades have mostly nu E, tracks have mostly nu mu, double cascades have mostly nu tau, but there's a cross correlation between the different flavors as well. So it's not completely one-to-one, but it can tell us quite a lot about the flavor structure. And the events that IceCube has seen in the public 7.5-year data release look a bit like this. So in yellow here, we have the cascades, green are the tracks, and the browner spots are the double cascades. There's only 4 of those actually, so not too many if you're trying to spot them. And as we can see, it's mostly cascades, so we're expecting kind of mostly electron neutrinos off the first bat. So what I want to recover is the flavor fluxes. How do we do that? I need to write a model for this. And first, well, I write it like this, and I'm going to explain to you the different components. First, we have the all flavor flux. So this is the behavior of all the neutrinos put together. Then we introduce the flavor ratio of that's now flavor dependent. So you can think of this as like total number of neutrinos, fraction of those neutrinos that are flavor alpha. And in the standard picture, we would only have the one here. So this term that I introduced here, which I call the anisotropy term, would, where my angular dependence is captured, would be completely 0. So if we recover a sky map of what the flux looks like, and if we just take a look at this anisotropy term, it would look exactly like this at 0, which is this darker color here. But we can expand that term, and we can basically decompose it into spherical harmonics using some anisotropy coefficients that are flavor dependent, and then using the real valued spherical harmonics as a basis. And with this, we can capture any anisotropy that we can see in the flavor structure. Using this, we fit it to the IceCube data to recover the flavor fluxes. And we can then ask the question of, are flavor ratios directionally dependent? You may have seen I said new physics can cause these anisotropies. And I want to kind of delve into a bit and justify why we think that. So, of course, the detection process can cause us to see anisotropies. The IceCube map itself didn't look completely isotropic, but we try to account for these effects using data and Monte Carlo. We use a lot of computational resources to make sure that all of these effects of the Earth attenuation and everything else that can account for this are, in fact, removed. And that's my problem. So assume we've all done our good job, assume that the Monte Carlo works well, and assume that my analysis is good. We can then move on to what else could cause these anisotropies if we then do see them. And we can propose some sort of production mechanism. We know that the universe is roughly homogeneous and isotropic, but we also know that IceCube does look for point sources, and Damiano talked a bit about this. But even with that, we care here about the flavor ratio. So we care about the flavor structure. And at the end of the day, even if you propose some anisotropic source distribution, you don't expect your flavor ratios to be directionally dependent. So you don't expect different production mechanisms to be anisotropic. And that's what we're trying to capture. I'll actually come back to that sentence in a bit. And that leaves effects that you can gather during propagation. What can modify the arrival direction? What can modify the distributions during propagation? Lots of stuff. Dark matter interactions. You can have some sort of secret interactions. And my favorite thing to look at is Lorentz invariance violation. I'm going to go a bit into this, but that can actually generate some quite fascinating anisotropies. This is all new physics, which is why I said this is a great way to look into new physics. I need to speed up a bit. Sorry about that. So just to introduce real quickly, Lorentz invariance violation, you propose a second Hamiltonian that couples to the momentum 4 vector of the neutrinos. You decompose that at the Hamiltonian level into spherical harmonics. I'm not going to go too deeply into that, except to say that even if you just turn on a dipole term at the Hamiltonian level, the behavior of the neutrinos, of the flavor ratios that you get is not a dipole. This is very, very complicated stuff. And it depends on how exactly you parameterize this. But they look really, really interesting, and you can generate some pretty interesting anisotropies with this. So what do we actually see with the IceCube fits currently? So again, these are my anisotropy maps. This is what they would look like if in the standard picture, if everything was completely isotropic. These are the current best fits. Don't worry, these look significant, but they're all compatible with isotropy at 1 sigma. So just to give you a scale here, so the darker saturated colors means flavor overabundance for electrons in this case. The lighter colors means underabundance, and black is the mean flavor, the value where we have the mean flavor ratio. To come back to that sentence of we don't expect different anisotropies in the flavor ratios, that means that we actually expect the differences between these two maps to be completely isotropic. So we can define a new quantity just by taking their difference. And in the standard picture, again, it would look exactly like this. And this is the best fit. Again, compatible with isotropy at 1 sigma. But we want to see, because this is the best avenue into looking at these new physics effects, how well can we constrain this parameter? So how well can we constrain this anisotropy over time? And for that, we did some future predictions accounting for different detection scenarios. We looked at the detectors starting here. So down here, we have the year of observation, and the detectors basically start from the point where we would first get data from them. And we accounted for several, we did 3 detection scenarios, so basically just IceCube, IceCube plus Gen 2, and then all of these detectors. And all of these detectors, of course, drive your better statistics and get rid of your attenuation due to the Earth, because they kind of cross-compensate for each other, which is really nice. And to give you a bit of a sense of what the scale on the y-axis is here, this is the current value of the best fit. The bar here is the 1 sigma. 0 is isotropy. And on the y-axis is actually the power spectrum evaluated at the dipole. If you don't know what that means, don't worry. This is what isotropy looks like, and the further you get up the axis, the more anisotropic it gets. So just keep that picture in mind. So what do we actually see? If we only keep going with IceCube, we see a 25% improvement. So we go from a map that looks like this, that we can't distinguish from isotropy, to a map that looks like this by 2040. If we then add Gen 2 at the appropriate time, this is what the map looks like. And we get a further improvement. If we add all of the detectors, this is the map that we recover. So again, this is what we can see now. This is what we can not distinguish from isotropy by 2040. It's quite a bit of an improvement. And this analysis was done just assuming IceCube-like sensitivity in all the detectors, so we didn't do much complicated modeling for each of the different detectors. Further questions to ask for now is how anisotropic is, for example, Lorentz invariance violation, where on the power spectrum here, can I draw a line that says this is what LIV predicts? And what about other beyond standard model anisotropies? And can we actually use these flavor ratios to constrain them? And that is currently what I'm working on. So hopefully by the next time you see me give a talk, I'll have an answer to that. Oh, sorry.
Other questions? So this might be a bit far-fetched, but so I have a colleague that is doing probability case, spectral analysis, and there you can change the shape and also test for Lorentz variance violation. Can you compare other bounds, for example, from probability case with respect to shape to your Lorentz invariance checks? Is this compatible and comparable somehow?
I think it depends on how you write your Lorentz invariance. So in our model, we're using the standard model extension, where this is parametrized with the sort of harmonic expansion at the Hamiltonian level. If we're looking at the same parameters the same parameters in that Hamiltonian can drive spectrum changes, but they can also generate angular anisotropies. If we're basically speaking the same language in that setup, then we can compare them. And there have been bounds on these LIV parameters also from cosmic rays. There's side wheel analysis. So in principle, yes, but we really need to make sure that we're putting bounds on the exact same thing. So for example, to say another thing about that, in order to the current bounds are made in the reference frame of the sun. So if I want to make bounds from our observations, I also have to rotate into that reference frame. Otherwise, I'm not comparing like to like. So probably it's a quite complicated theory.
Okay, thanks.
Yeah.
No questions? I was wondering so the difference that you see, this was actually based on the data, the difference between phi e and phi tau.
Yep.
Phi mu.
Phi mu. Yep.
So that's mostly in the north-south direction.
Yes.
And this is the equatorial system. So this, the events itself, they already have like a north-south anisotropy, right?
Exactly. Yeah.
Yeah. So how sure can you be that this is not maybe some misidentified local effect from event selection? So you thought about that?
I mean, that goes into it a lot. There's two things about that. Again, these are just the best fits. So when I actually take a look at, you can generate a curve of all the fits. This is completely isotropic at 1 sigma. So it's not too far away from that actually.
So this is included in the 1 sigma value.
Yeah, exactly. So with maps, it's really difficult to show where the 1 sigma region is. That's kind of one thing. Another thing is we did some validation with how we do our fits to make sure that if we assume an isotropic flux model, and then we use the Monte Carlo to predict what this would look like as an observation in IceCube, and then we try to basically recover, okay, from that, can we recover that our flux model is isotropic? That works relatively well. That's sort of validation method that we used. But you're absolutely right, especially because the north-south asymmetry is driven by the muon map mostly, which is where we have the least amount of events in the tracks. And there, I mean, I can't say that I'm confident that this is what nature actually looks like.
Also decompose basically the horizontal one, but only look for the horizontal one, which doesn't have this north-south.
Yeah, so we actually try to recover all 3 of the basis ones. Yeah, and then we combine them to make the picture. Yep. But you're absolutely right. And another thing that you could do is just disregard the north-south dipole and then just look at the azimuthal distributions. I mean, I don't actually have a good sense of if that's throwing away information that you might want to keep or if it's just getting rid of. Yeah. Well, we can talk about that. Yeah.
Okay, I don't see any other questions. Thank you again.
Yep.